Hey everyone, Mix McCarston here. I'm going to talk you through assignment 8.2. So the first thing you want to do, you obviously found it on Schoology. Okay, so in Schoology, you have an attachment. Okay, and you want to put this into Notability. Okay, looks like this. Okay, you're going to put it into Notability. All right, you're going to get to Notability. Find your 8.2. All right, and you want to split the screen. Okay, so you want to split the screen. You want to have half of your screen being 8.2, interpreting graphs in Notability, and the other half being this video on Schoology.
All right, so the first thing we're going to do, you don't need to write anything down. We are just going to watch a video. I might pause it sometimes to ask some questions as you watch. So you're paying attention to this video.
Today I want to ask you a question. Have you ever thought of graphs as stories? Yes, you heard correctly. Graphs can tell stories about all sorts of things. And today I want to tell you two stories with my graphs. One which has a very happy ending and one which is not so happy, unfortunately. This is the story of two athletes running at the Olympic final 100-meter race. Try to imagine them there, in the Olympic Stadium, surrounded by thousands of excited fans who cheer for them as they prepare to begin the most important race of their life.
Okay, so let's notice a few things after 8.1. All right, we have distance on our vertical up and down y-axis, and that's measured in meters. Then we have time over here on our x, our horizontal, our flat axis, and it's measured in seconds.
These two young men have trained for months for a few seconds of glory, and this is the moment they have worked so hard for. Then the sound of the starting gun reaches their eardrums, muffled by the deafening sound of the crowd that stands and jumps along the innumerable rows of seats that surround the stadium in delirium. But these two athletes are focused on only one thing: the finishing line, 100 meters away, but that seems so far. Both sprinters put all their effort in this race, but one of them takes the lead immediately. The green.
Okay, so we see the two runners take off, okay, at the beginning of the race. The green runner here and the red runner here. The green runner is ahead. They're running this way and the finish line is here. The green runner is ahead, meaning this runner is running faster. So let's take a look at our graph. Okay, we have two lines, one for the green runner and one for the red runner. And the green runner is running faster. So what do you notice about these two lines? What's different between these two lines? This one is running faster, has a higher speed, and this red runner is behind, is running slower.
Runner has already reached the 50 meters line. He's ahead of the race. He's going to win. In fact, he's so much faster than the other runners that he's not only going to win the gold medal, but if he carries on at this pace, he's going to smash any world record in history. In fact, he's going to finish the race in just about 7.5 seconds. Now, I don't even know if this is humanly possible, but play along with me for a minute and try to imagine the growing excitement of this athlete as he sees the finishing line approaching. But something terrible happens. The green runner, the one who was going so unbelievably fast, who was undoubtedly going to win the gold medal and become the pride of his nation, falls. And that's when the red runner sees his chance.
So the green runner was running faster and the green runner fell. And notice what happened to our graph line. It was running fast, seconds were passing and he was also moving a distance, and then he fell down and stopped moving. The time, the seconds, 3, 4, 5, 6, 7, 8, they keep counting, but he is not going any farther. He is not moving any more distance.
A fraction of a second earlier, he had given up all hope. He's too fast, he thought. I'm never going to reach him. But now everything is different. The red runner carries on as fast as he can, seeing himself on the podium, holding his gold medal in the air, proud to be the first gold medalist in the 100-meter race from his country. This is going to be the best day of his life. The red runner crosses the finishing line.
Okay, so the red runner saw the green runner fall right here and kept running until he got to the end, the 100-meter mark. Then his line changed. It changed its slope. It changed how steep it was. Okay, so it was steep and then it got less steep. Okay, it got slower. He got slower and then he stopped because the race was over.
First, with a sigh of relief, then slows down and stops and remembers the falling sprinter. He, the unfortunate green runner, lost a lot of ground, and in his fall he can see all other athletes running past him. He has lost about 4.5 seconds and the race is over for him. But as a true winner, he decides to finish the race. So he stands up and begins to run again.
Okay, so he fell down. He saw the end of the race, but he's going to finish anyway. So at second 8, okay, he starts running again. He starts running again. He is running, so he's traveling more distance over these seconds that are passing.
As fast as he can, with pride and with tears that start blurring his sight. He finally reaches the finishing line. He can stop now, sit down, cover his face.
So he gets to the finish line, which is at 100 meters. He slows down, then he stops.
And cry bitterly. His graph tells a very sad story, because this athlete will be too old to compete at the next games, and his accident stole away the dream of his life, a dream that was almost achieved a few seconds before.
So this is the story told by the graph. All right, so now you want to have 8.2 open. Okay, 8.2 open and this video split screen. All right, so we are going to look at some graphs. Maybe they tell us some stories, just like in the video. Okay, so we have 8.2 interpreting graphs. Follow along with this video, that's happening right now, 8.2, and fill in the notes with the video. At the end on page 4, there's going to be some questions that you're going to answer on your own, and then you'll turn this assignment into Schoology when you're done. All right, so we have a graph. Okay, we have a graph right here, and it has a one line on it. Okay, this blue line. So number 1, the blue line shows, what is that showing us? That is showing us a constant speed. Okay, a constant speed. Okay, we want to zoom in a little. Okay, constant speed. So add that to your notes. Okay. Constant means what? What does constant mean? Okay, constant means that something is staying the same. Okay, constant means that something is staying the same. And let's remember our equation from last week. How do we find speed? How do we find speed? All right, speed equals distance divided by time, right? So if we look at our graph, okay, if we look at our graph, we do have distance and we have time. So this line is showing us our speed. Okay, let's take a look at this graph. We saw this happen to the green runner, okay, when he fell down. So we had time passing, okay, but no distance. The distance is not changing. It is staying the same. Let's take a look at our graph. Our distance has an m at the end of it. So if I ask the m means, what does the m mean? The m stands for meters, and it's the unit that we measured our distance in. Okay. Number 6, the distance is measured in, oh, I gave you that answer early. The distance is measured in meters. Okay. The S here, what does our S stand for? Our S stands for seconds. Our S stands for seconds. And this tells us that time, because it's right next to time, is being measured in seconds. Okay, good. Okay, and this line is flat because, why is this line flat? Let's think what happened when we saw a flat line in the story. That meant the runner fell down. The runner was not moving. Okay, so when we see a horizontal left to right line, a flat horizontal line, okay, this means that no distance is being traveled. Okay, the line is flat because no distance is being traveled. There is no motion. Okay, time is passing, but there is no motion. There's no movement. Okay, so when we see a flat horizontal line, that is what it means. All right, now we see a graph with 2 lines. It kind of looks like the beginning of our race from the video. We have our distance here, and then it says km next to it. So the km means, let's think about our units that we measure distance in, and km stands for kilometers. Kilometers, okay? Now 11 says, what is the distance of the green line at 2 hours? What is the distance of the green line at 2 hours? So on our x-axis, we have time in hours. So here's 0 hours. Here's the green line at 1 hour. And at 2 hours, we follow up and it hits this distance right at 40. Okay, right at 40. And we're not just going to put 40, we need to have a unit. So 40 what? 40 km, 40 kilometers. Okay, 40 kilometers. Okay, what is the distance of the red line at 2 hours? The red line at 2 hours. So we go to 1, 2 hours. We follow the 2-hour line up and look over at our distance, and we see it is 20. 20 kilometers, because we have measured in kilometers. 20 kilometers, and we abbreviate kilometers with a km. Now it's asking to look at these 2 lines. Which line shows a faster speed? So let's think about the beginning of our race. The green runner was ahead of the red runner. So the green runner was running faster than the red runner. So the green line is showing a faster speed. Our green line is showing a faster speed. Awesome. Okay, now we're going to get a little more complicated. We have some more lines. Okay, let's look at another graph. What does this graph show us? So we look at our labels. We have distance, m, which means distance in meters. We have time in seconds. Okay, and we have seconds along here on our x-axis and meters on our y-axis. And we have a key over here. It tells us red, so this red line means biking. This green line is skating, and this blue line is walking. So let's read a little about this graph. This graph shows us the distances and times 3 people traveled or moved. Each person used a different way to move. One person traveled by bike. This person's movement is shown in the red line. One person traveled by skates. This person's movement is shown in the green line. One person traveled by walking. This person's movement is shown in the blue line. One question for you: what does the vertical line of the graph, the up and down, show us? The vertical line of the graph shows the distances that people could travel. The distance units are meters, or m. The distance starts at 0 and increases to 70. Each box, okay, increases the distance by 10 meters on this graph. Okay. What does the horizontal, the flat line of the graph show us? The horizontal line of the graph shows the times the people could travel. The time units are seconds. The time units start at 0 and increase to 7. Each box increases time by 1 second. What do the 3 lines on the graph show us? Each line on the graph shows the time and distance each person traveled. So our red line shows the biker's time. Okay, this red line. The green line shows the skater's time and distance moved. And the blue line shows the walker's time and distance moved. All right. How does someone make the 3 lines on the graph? If you were trying to make these 3 lines, how would you do that? So people make the 3 lines, or any line on a graph, by measuring the movement of each person. These measurements are called data, or information. People use timers, rulers, and other tools to get this data. Today, these tools are often electronic or digital. These tools measure time and distance. Then, people plot or put this data on the graph. Sometimes a machine plots the data for the people. So that's how we get those graphs. So let's take a closer look here at some of the parts of this graph. I'm going to turn a light on. There we go. Okay, let's look at each person's movement and compare the 3 people's movements. What do the lines on this graph tell us about movements of the 3 people? Okay, what do we know about the biker's movement by looking at the red line? We can ask, how far did the biker move in 6 seconds? So we find our 6 seconds and we trace it until we hit the red line. So in 6 seconds, the biker traveled 60 meters. 60 meters. So we can say 60 and then m for meters. How far did the biker move in 1 second? So we look at our 1 second spot. We trace it until we hit the red line, and we see that the biker moved 10 meters. The biker moved 10 meters. Okay. What is the biker's greatest distance traveled? What's the farthest that the biker went? So our graph stops here. The farthest the biker went is 60 meters. Okay, what is the biker's greatest time travel? What is the time, the longest time? What's the time the biker spent biking? So we look at our time and we see it is 6 seconds. All right, now let's take a look at our green line. What do we know about the skater's movement by looking at the green line? How far did the skater move in 6 seconds? So this is the same graph copied here. So our green line in 6 seconds, we hit the green line and go over to distance, and we see that in 6 seconds, the skater moved 20 meters. 20 meters. How far did the skater move in 1 second? We look at our 1 second, go up to the green line. This one we hit in between the numbers, so we kind of have to make a little guess. Okay, we estimate. So I would say that is about 3 meters, maybe 4. Let's say 4 meters. Okay, 4 meters in 1 second. What is the skater's greatest distance traveled? So we take a look at our green line, and the skater made it 20 meters before stopping. 20 meters. All right, what is the skater's greatest time traveled? So how many seconds did they travel for? And we see they stop right at 6 seconds. So 6 seconds is our time. So our next one is about our blue line. What do we know about the walker's movement by looking at the blue line? How far did the walker move in 6 seconds? So we look for our blue line, and we look for our time of 6 seconds, and we go until we hit the blue line, go over to our distance, and we see it is 10. So that is 10 meters. 10 meters. How far did the walker move in 1 second? Okay, so we go to 1 second, and we're going to have to estimate. We said our green line was 4, so let's say this is 3. Let's say 3 meters. 3 meters. All right. What is the greatest distance the walker traveled? We look here. The farthest they went stopped here, so our greatest distance is 10 meters. What is the greatest or longest time the walker traveled? So the walker traveled for 6 seconds and then stopped. So 6 seconds. I have to put this one down here. All right. Well, we can fit it on that line. Okay. Six seconds. Okay. Now, let's compare the distance and time traveled by the 3 people. What are the longest distances each person traveled? Okay, the longest distances. The biker's longest distance was 60 meters. The skater's longest distance was 20 meters. And the walker's longest distance was 10 meters. Which person traveled the longest distance? Which person? The biker, the skater, or the walker? Yeah, 60 is our biggest number, so our biker traveled the longest distance. Which person traveled the shortest distance? Who did not get as far? Our shortest distance is 10 meters, so that would be the walker. What are the longest times the three people traveled? Our longest times for our biker is 6 seconds. Our skater is also 6 seconds, and our walker is also 6 seconds. So for each of them, they each traveled for 6 seconds. 6 seconds. And our walker traveled for 6 seconds. Okay. Which person traveled for the longest time? This one's kind of a trick question. None of them, right? They all traveled the same time. They all traveled for the same time. They all traveled for the same amount of time. Okay, none of them walked longer. They all walked for 6 seconds. Why did the biker, skater, and walker all travel the same amount of time but different distances? So the same amount of time but different distances. Why would that be? They travel different distances. You can see our lines have different slopes or steepness. Okay, so that means our biker traveled the farthest in the shortest amount of time. So the biker is traveling faster. So why did they all travel the same amount of time but different distances? Because the biker was traveling faster than the skater and walker. Right? You may have written something a little different, but that's okay. So let's compare the lines on the graph. Why is each line straight? Why is each line straight? It doesn't change. It just keeps going in a straight line. Okay, if we remember from the beginning, we saw a graph with one line, and we talked about how that graph had a blue line, and it means it is a constant speed, which means the speed is the same the whole time they're traveling. So why is each line straight? Each line is straight because they are traveling at a constant speed. Their speed is not changing. They're not speeding up or slowing down. This one has a few answers. How are the three lines on the graph different? How are they different? They're different colors, but what else? Okay, the red line is steeper than the green line. It is steeper. Okay, the green line is steeper than the blue line. Okay, that's how they are different. Our next question says, why is the red line steeper? Why does it have a greater slope than the green and blue lines? Let's think about what we learned about how fast they were traveling. We said, why did they travel the same amount of time but different distances? Because the biker was traveling faster. So when you have someone traveling faster on a graph like this, that means their line is going to be steeper. So the red line is steeper because the biker is traveling faster than the skater and walker. The biker is traveling faster than the skater and the walker. Awesome. So now you're going to do some practice on your own. So here's a new graph, okay? A blue line and a red line. We have a walker is the red line and a blue line is running. So you're going to answer questions 1 through 10 on your own about this graph. When you are done, you're going to turn this in to Schoology.